Finally, we reached the borewell where we are about to do resistivity logging. Kindly note that the resistivity logging could be done only in the borewells which contains water. So before going for logging, we must check whether the borewell has water or not. If it doesn't have water, then it is not suitable for doing resistivity logging. The reason is we are going to insert a resistivity probe into the borewell, and this probe requires water as a medium to conduct current through the surrounding formations as well as receive apparent resistivity readings from those formations. This condition is only for resistivity logging. Gamma logging doesn't need water. It can be done in an empty borewell. In our borewell, the water level is at 8.30 meters. But before doing logging, we can see the instruments inside the van and make some initial connections. And this is the front view. We have the DMPL 3 digital multipurpose logger 3 instrument on the right and the speed controller unit which is on the left. So these are the two instruments, and behind the instruments we have a winch and a motor, and this is the back view. Behind the DMPL 3 instrument we have two connections, one is to the winch and the other to the generator. The two generator slot is connected from below the table to the switchboard, and two winch slot is connected to the winch here. And then behind the speed controller unit we have three slots. One is for the motor, the second one for the generator, and the third one for the battery. So first, two motor slot is connected to the motor right here. It is connected to the motor, and then to the battery has a small wire connection to the vehicle, and this is used to run the motor from the power supplied by the vehicle battery during emergency purposes, but it is always advised to do logging in generator mode only. Next, the generator slot is connected to the switchboard, and this switchboard receives power supply from an external generator. This is that external generator which is the power source for doing resistivity logging, and it runs in petrol. The plug from the vehicle is connected to it. Also, the generator is kept on the ground. We have our resistivity probe as two segments or pots inside these PVC pipes, and we need to connect these two pots into a single resistivity probe. This one is the depth encoder or depth counter, which simultaneously measures the depth of the borewell when the probe is moving down in the bore from the top up to the total depth. And this depth counter has a tripod like arrangement. They have given three short tripod legs and three long tripod legs. Shorter ones have screw like structure at the top, and it is screwed into the holes of depth counter, and we can increase the height by attaching the long legs. And these two short and long legs have holes. It should be aligned, and then we can insert a screw and tighten it with a nut, and now depth counter tripod assembly is fully set. Now this entire depth counter tripod is taken and kept just above the borewell, and it should be aligned straight to the connector of the winch which is inside the vehicle, and we should make sure that the surface is flat and the tripod assembly is intact so that it won't collapse during the logging process. And one person is required to hold this tripod setup to avoid collapse due to unexpected disturbances during the logging process. Kindly make sure that the calibrated wheel is aligned straight to the connector of the winch inside the vehicle. It should be in a straight line, and also the wheel should be straight above the borewell so that it would be easy to insert the resistivity probe into the borewell after connecting to the winch. Now we are connecting the two parts of the resistivity probe. The larger part has the probe head with sensor, which is to be connected to the connector in the winch. Before that, we can connect these two parts of the resistivity probe, and it is very simple. We can connect these two parts by screwing mechanism like this. We just need to screw it fully, and after that we need to tighten it with the help of this spanner like this. And then this connection is sealed with the insulation tape so that water won't enter inside the probe. Next, we are going to connect the connector of the winch to the probe head with sensor, and while connecting this, make sure that you hear a tick sound, which makes sure that the connection is perfect, and then we can screw the connector and tighten it with the spanner. Now the connection is made, and this probe head connection is also sealed with the insulation tape to make sure that the water won't enter inside the probe. After sealing, the resistivity probe is kept aside for a while, and then we are taking a long wire and we are connecting this depth counter to the DMPL3 instrument inside the van. So we are connecting here, and then we are taking this wire and connecting it to the slot in DMPL3, and it will be written as 2 depth counter, and we are connecting it in this slot. And now we are connecting a red colored wire to the C ground, and then it is connected to the winch with red wire. So this is C ground. Now we are going to hammer the C ground current electrode at a distance of 15 to 20 meters from the borewell. In our case it is 20 meters and it has been already measured. So after hammering we are connecting the red wire, and this is the C ground electrode at a distance of 20 meters from the borewell. Now a black wire is connected to the P ground, and again it is connected to a winch with yellow wire. Now the P ground or potential electrode is hammered at a distance of 5 meters from the borewell. And now the yellow wire is connected to this P ground electrode. This is the P ground electrode at a distance of 5 meters from the borewell. And next we are inserting this resistivity probe into the borewell through the calibrated wheel of the depth counter. So when the resistivity probe is completely inserted into the borehole and the probe head is at the ground level, we need to press the button in the depth counter so that the reading will be set to 0. Now it is set to 0. Now we have switched on all the switches in the switchboard. When the generator is switched on, we get the power supply to the switchboard, to the speed controller and DMPL instrument. And then we need to switch on the DMPL instrument first and then switch it to resistivity logging mode. Now we need to open the laptop which is connected to DMPL3 instrument, and we have Well Logger FU software we need to open it and then select new logging. As we are going to do down logging, we keep it in down log mode and then select new file option and then give a file name. I am giving vtech and then give all other details and then click save info. So after clicking save info, we can switch on to logging graph mode by clicking the logging graph tab next to information tab, and then in here we need to click the start button. When we click it, it will be highlighted. Now we are switching on the speed controller unit and pressing the switch down for downlog mode, and then we are increasing the speed very slightly. Now we can see that the winch is rotating and the resistivity probe, it is going down inside the borewell. Meanwhile, in the well logging software in this laptop, we can see that the depth value is increasing gradually as the probe is moving down inside the borewell. We will start to get the apparent resistivity readings only when the probe head and the current electrode touches the water. Here we are starting to get the readings from the depth of 8.30 meters, which is the water level. We will be getting 4 readings and 4 graphs, and these are short normal, long normal, lateral and self potential readings. Now the depth counter is showing 28 meters and the resistivity probe is moving at the same rate inside the borewell, and also in the software we can see the graph is being generated depthwise, and it is also showing 30 meters. And now we are getting a signal to stop as the probe reached the total depth at 33.2 meters. To stop the winch, we have to switch it to the middle position like this. Also we can notice that the graph generation stops at 33.2 meters. Now click stop and then click the save graph button so that the graph will be saved. Now let's close this, and now we can do uplogging. For this we have to open the well logging software again and click new logging. Now we have to switch it to uplog mode. Now click new file and give a file name vtech002 I am giving, okay, and then you can give other details. Here I am giving the exact well depth as 33 meters. After giving them, click save info and then we can go to logging graph mode and then we can click the start button. Now in the speed controller unit we have to switch it up in the upper position for uplogging. Here we can notice that the depth value is in minus values and it is increasing, which means the resistivity probe is moving upward as it is being uplifted from the borewell. Also we can notice that the winch is rotating in reverse direction and it is uplifting the probe. In the depth counter, the depth values will be decreasing. You can notice this. Meanwhile, in the well logging software, the graph will be generated gradually as the resistivity probe is being lifted inside the borewell. Here the graph is not visible because we need to scroll the scroll bar below to the left, and we didn't do it during the logging process, so the graph is not visible here. But however, we can see at the top that we are getting readings for short normal, long normal, lateral and SP. So there is no problem. It will be saved properly, and when the depth is minus 33, the resistivity probe will come out of the borewell. So when the reading is 33, we need to stop the winch, for which we need to switch it down to the middle position in speed controller unit. Now we can see that the resistivity probe has come out of the borewell. Now in the well logging software, click the stop button and then save graph and then close. Now the uplogging data and graphs will be saved properly. And next, in order to ensure that the uplogging data has been saved properly, I am again opening this well logging app, and here I am choosing log from file option and then clicking the open file option, and I am choosing that uplog data vtex002, and we can find the graph. So the data and the graph has been saved properly, and you can also notice that the depth value starts from right and ends in left side. As we can see, the values 0 to 30, that is from right to left. This will be in the case of uplogging, while in the case of downlogging, the depth readings will be from left to right. And if we compare downlog and uplog data, the uplog data is more reliable and appropriate. This is because during uplogging, the cable will be straight and the probe will be intact and uplifted at a same rate, so that the measurements are appropriate compared to downlogging. So it is always advised to take uplogging data for interpretation, and for interpretation we have another software in which we can view these graphs in a vertical view, which will be more easy for interpretation, and the name of the software is LoggerApp VER4. So as we have completed the logging, we should disconnect all the connections inside the van, and also while the van is on the ride, everything should be disconnected, as the jerking of the van may cause damage to the cables or the connecting slots in the instruments. So after logging, we should disconnect everything, including the resistivity probe, and place it in the PVC pipes, and everything should be disconnected and kept back in their original locations. So as we have collected the logging data, the next step is interpretation. For doing interpretation, we should know the working principle of this DMPL3 or Digital Multipurpose Logger 3 instrument, and let's see that now. So our resistivity probe is immersed into the water inside the borewell, and from the top we have the connector from the winch, which is connected to the probe head, and next to the probe head we have the current electrode, and we can name it as A. Commutated direct current is supplied to this current electrode A, and here the current passes between the two current electrodes, A, which is in the resistivity probe, and B, which will be in the ground 20 meters from the borewell, which is the C ground. And this current will pass through the surrounding formations evenly in all the direction in a spherical shape. As already said, the resistivity probe requires water as a medium to conduct current through the surrounding formations. And next, below the current electrode, at the distance of 16 inches, we have our first potential electrode, which is the short normal, and we can name it as M1. This DMPL3 instrument works based on the well-known Ohm's law, which is V equal to IR, where V is the voltage, I is current, and R is resistance. So the basic concept is that the voltage drop is measured between the potential electrodes. So in our case, we have the first potential electrode M1. So the potential drop is measured between M1 and N, which is the P ground electrode. at a distance of 5 meters from the borewell, which is on the ground. So based on the voltage drop, the DMPL3 instrument will measure the resistance, and from the resistance it will measure the apparent resistivity of the surrounding formations using the Ohm's law formula. Also note that the depth readings which we get in the well logging software is the depth at which the probe head is located at the borewell, which I have shaded in the video. However, we will start to receive the short normal, long normal and lateral readings and graph only after the current electrode A touches the water. The distance between the probe head and the current electrode A is just 4 inches, which is very negligible. Now as the short normal is at the distance of 16 inches from the current electrode A, the radius of investigation is also 16 inches from the center of the current electrode A. This means we will get the apparent resistivity readings of the surrounding formations, which is within the radius of 16 inches from the current electrode A. The depth of investigation is also 16 inches for the short normal electrode. This means we are getting the apparent resistivity reading for the formations which are within the depth of 16 inches from the current electrode A. So we will receive a single apparent resistivity reading for this cylindrical volume of the surrounding formation of 16-inch radius as well as thickness from the current electrode A, which is shaded in this video. Below the short normal electrode M1, we have the connection between the two parts of the resistivity probe. We won't receive any readings from this part. And next to this we have the second potential electrode, which is the lateral electrode, and it is named as M2, and it is at a distance of 48 inches from the current electrode A. So from this lateral electrode we will get a single apparent resistivity reading for the cylindrical volume of the surrounding rocks of radius 48 inches as well as depth 48 inches from the current electrode A. Next, below M2 we have the third potential electrode, which is the long normal, and it is at the distance of 64 inches from the current electrode A, and this could be named as M3. And from this long normal electrode we will get a single apparent resistivity reading for the cylindrical volume of formation of radius 64 inches as well as depth 64 inches from the current electrode A. Now we can understand that at any particular depth inside the well we are receiving apparent resistivity readings from the short normal, long normal and lateral potential electrodes for various volumes of surrounding rocks, and this volume depends upon the distance of that particular potential electrode from the current electrode A. If it is a short normal, it is 16 inches, the long normal is 64 inches and the lateral is 48 inches. So from this we can also understand that the rock formations with lesser thickness could be demarcated only from the short normal data, as it provides a single apparent resistivity data for a lesser thickness of 16 inches. Now for an example, let us consider we have a quartz vein of 18-inch thickness in hard rock terrain, and this is a very small layer, and this could be identified only from the short normal data, because the long normal data will show a single apparent resistivity reading for the thickness of 64 inches. So these formations with lesser thickness and thin formations will be left unnoticed in the long normal data. So this is the main significance of short normal data, from which we can demarcate rock formations of lesser thickness. But in the short normal data, the radius of investigation is also very small, that is 16 inches. While in the long normal data, the radius of investigation is more, that is 64 inches. So with respect to the radius of investigation, the long normal data serves good, and in case of hard rock terrain, mostly we will be having homogeneous rock formation for larger thickness. Thin bands of rock formations which are less than 64 inches are very rare in hard rock terrain area. And in the 4 districts which is pertaining to Tirunelveli groundwater division has mostly hard rock terrain, and we have only few sedimentary terrains like the Sathangulam and Pannambarai sandstone area, and the thickness of these sedimentary beds are only 10 to 20 meters from the ground surface. In our districts we have majorly hard rock terrain which have fractured zones or jointed zones as well as weathered zones, and the thickness of these zones will be usually more than 3 meter. The long normal data provides apparent resistivity for 64 inch thickness, which is 1.6 meter or 160 centimeters, and thus this long normal data is suitable for demarcating and interpreting the depth-wise lithology of hard rock terrain area. But we must also see the short normal data to demarcate and identify thin layers below 64 inches or 1.6 meter. It may rarely occur in hard rock terrain like the quartz veins or some intrusions of igneous metamorphic rocks or the clay formations, and mostly it will be more than 1.6 meter thickness. But however, we can see the short normal data to find out if there is any thin layers in the hard rock terrain, so that the interpretation will be more accurate if we integrate both short normal and long normal data. And one more data which we obtain is the SP data, which is also called as the self potential or spontaneous potential data, and this data is the measurement of natural potential difference between the potential electrode in the resistivity probe and the potential electrode which is at the ground, that is P ground. This potential difference occurs due to the movement of ions from Borewell fluid into the formation fluid or vice versa along the permeable formations, due to which natural current is produced, and this current is usually very small, and it is measured in millivolts, and thus the SP readings are in millivolts units. And in our resistivity probe, the SP values are received from the short normal electrode, which has a small sensor to record the natural potential difference, and this SP data is used to only identify the permeable layers, but we cannot measure the amount of permeability of these layers. We can only identify whether a layer is permeable or not from this self potential data and graph. And this SP data is also used to identify the formations having saline water, and also to identify clay beds. And this is all about working principle of digital multipurpose logger 3 instrument, and next we are going to see the interpretation of the collected uplogging data. Major applications of resistivity logging data in hydrogeological studies is that we can interpret the depth-wise lithology of the borewell, and we can identify the permeable zones in the borewell, and also we can identify the freshwater and saline water formations in the borewell. As in our case, we are dealing with hard rock terrain. While interpreting the lithology, we can demarcate the weathered zones, fractured zones, jointed zones, and massive zones. So we should note that all the fracture zones won't supply water to the borewell. The fracture zones which is having a high hydraulic conductivity could only supply water to the borewell. So these highly potential groundwater fractured zones can be identified using this resistivity logging data, and also we can identify the permeable zones in the borewell through which water enter inside from the surrounding formation. So in the resistivity logging data, we are getting apparent resistivity of the rock formations in ohm meter units. So electrical resistivity means it is the ability of the rock or any material to resist the flow of electric current. So for each rock type, we have a specific range of resistivity readings in ohm meter, which is shown in this chart, and we can interpret the resistivity logging data by comparing the resistivity readings with the chart, and we can find what is the rock type at a particular depth. In our case, as we are dealing with the hard rock terrain, it will be mostly igneous and metamorphic rocks, as well as it will be a weathered, jointed, fractured, or a massive igneous or metamorphic rock. So in this chart we can see that unweathered massive igneous rocks resistivity value ranges from 1000 to 100,000, and weathered igneous rocks ranges from 5 to 500, and weathered metamorphic rocks ranges from 10 to 5000. This chart also shows the resistivity values of sedimentary rocks. Below the chart we can find the conductivity values for all those rock formations. Everything which is related to hydrogeology, the resistivity readings are given in this chart, and we can use this for the interpretation of short normal, long normal, and lateral data which we get in this logging process. This table also shows the resistivity range for various rock types, and it is in table form. This could also be used for interpretation, and this table shows the resistivity range for various types of water, and this will also be useful for interpretation. And this table is for hard rock aquifer areas, and after demarcating the weathered zone, fractured zone, saturated fractured zone, and massive zones in the hard rock aquifer, we should compare the resistivity data of each zone in this table. For example, if the weathered zone has 25 to 100 ohm meter resistivity, and the fractured zone has 250 to 600 ohm meter, and the saturated zone has 80 to 350 ohm meter resistivity, and the massive formation has greater than 5000, then the groundwater prospectus or aquifer health is good. Likewise, we should compare the zonal resistivity in this chart and find out whether the aquifer health is good, moderate, or poor. Next, let us see the interpretation of self potential or spontaneous potential data, and this is the measure of natural potential difference between the electrode in the borewell and the electrode at the ground. I have already explained that this potential difference is due to movement of ions between formation fluid and borewell fluid. Let us now consider an example. In this figure, the formation fluid has high salinity compared to the borewell fluid, and compared to sodium, chloride ions has the highly moving capacity. So the movement of ions will be always from area of higher concentration towards area of low concentration. That is, the ions will move from high saline zone to low saline zone. So in this case, as the formation has a higher salinity, the chloride ions from the formation fluid will move into the borewell fluid. So due to this movement, natural current will be produced. Consequently, a potential difference is developed between the electrode in the borewell and the electrode at the ground, which is measured in millivolts. And if the borewell fluid has high salinity, then the whole process will be in reverse. So the main thing to note is that the movement of ions is possible only through the permeable layers. So at any particular depth of the borewell, if we find a potential difference, we can say that we have a permeable layer at that particular depth, as there is a movement of ions. Now let us see this SP graph. In order to interpret this SP graph, we need to draw the baseline, and this baseline is the line in which there is no potential difference, that is, there is no undulation. In this graph, the red line is the baseline, and with reference to the red line, we can see that there are some undulations towards left and some towards right, and these undulations are the indications of presence of permeable layers at a particular depth of the borewell. As already said, through the permeable layers there will be ion exchange between the borewell fluid and the formation fluid. This baseline could occur anywhere, either in the positive or in the negative millivolt readings. In the same way, the undulations may also occur in the positive or negative millivolt side. It doesn't matter. We just want to see whether from the baseline the undulation is towards the left or towards the right. If the undulation is towards the right side of the baseline, then it means that the formation fluid has fresh water compared to the water inside the borewell. The fresh water means it has less than 1000 milligram per liter of dissolved solids. So if the undulation is towards the right, then the water in the borewell is having more dissolved solids, more than 1000 milligram per liter. And the same way, if the undulations are observed towards the left side of the baseline, then it means that the formation water has more dissolved solids compared to the water which is present inside the borewell. In the above figure, it is given as salinity, but I am explaining in terms of dissolved solids. And also in the diagram, it is shown for shales and sandstone, but this same method is applicable for all the water bearing rock types and permeable layers. Now let's go for interpretation, for which I am opening this logging app VER4 software, and this is the well logging reporting software. I am clicking input files and then select input resistivity log data, and I am going to show the demo of the interpretation using the uplog data which I have taken for 100 meters in an irrigation well located in the Kurichikulam village of Tirunelveli district. And I am not going to show that VTech Industries borewell, which is only 33 meters depth, in which we cannot demarcate the many layers. It is fully weathered and some fractured zones are only available. But in this case, as we have done the logging for 100 meters, there are many layers to show a good demonstration of interpretation. So I am choosing this curriculum uplog data and click open. And now in this software, the graphs are displayed in the vertical view, which is easy for interpretation. Now I am clicking the resistivity log data at the left so that I can view that entire data, SP, short normal, long normal and lateral data at any particular depth of the borewell. And this is just a data view of the uplog data. And then again I am switching back to resistivity graph mode, and here the first step is to set the correct depth. So I am choosing the set depth, and then I am giving the maximum depth as 100. Click OK. Now the graph view has changed, you can see this. Now in this irrigation borewell, the water level was observed as 5 meters from the ground level. So we started to get the correct apparent resistivity values from the depth of 5 meters only, and we can observe that from the depth of 5 meters up to 100 meters, all the apparent resistivity readings are within 50,000 ohm meters. So now I am setting the resistivity value with maximum 0 and minimum value 50,000. Now you can see the resistivity graphs has zoomed in, and here also we can now clearly see that all the resistivity values from 5 meter depth falls within 5000 ohm meter. So we can again change the resistivity range as 0 to 5000 and then click OK. Now we are able to see the correct data in a zoomed in view. I am removing the lateral graph, which is the blue one, by unchecking it. Now we can only see this short normal, which is green, and the long normal, which is pink in color. The short normal is the resistivity data of the surrounding formation, 16 inches radius and 16 inches thick at a particular depth, and long normal is the resistivity data of the surrounding formation, 64 inch radius and 64 inch thickness at a particular depth of the borewell. So now I am zooming into a particular part so that we can compare the short normal and long normal graph. We can clearly see that in the short normal, which is the green one, there are more undulations, and in the pink one, which is the long normal, there are less undulations. So the short normal has a higher vertical resolution, and it is useful to demarcate thin layers of 16 inch thickness. Here we can see that from the depth of 15 to 22.5 meters, the short normal graph shows 2 undulations, whereas the long normal graph is a smooth straight line. This means that the short normal demarcates this 7 meter thick formation into 3 layers, whereas in long normal, as it is a smooth linear line, it is considering this 7 meter depth as a single layer without any demarcations. It is also observed that both the short normal and long normal graph has the same trend, only the resistivity value changes. That is, the long normal will have higher resistivity value than the short normal. Now I am zooming out to see the full graph, for which I am again setting the depth and resistivity values which we did before, setting the depth as 100 and setting the resistivity value from 0 to 5000. Now we have the full view of the resistivity graphs, and I am going to do the same for SP graph, for which I am going to set the SP values. As the natural current which we measure is very small, we can set it from minus 200 to 200 so that the graph looks good. We can also set it from minus 100 to 100 for more zoom in. So this looks better. Now we can just save this graph, for which we have to right click on the graph area and save as PNG image, and I am giving the file name Kurichikulam uplog, and then I am saving it. Now I am showing the graph which we have saved. Now I am going to demarcate the various layers depthwise in the borewell based on the resistivity data from the short normal graph and the long normal graph. As the water level is at 5 meters, we can identify the first layer from 5 to 10 meters, which has the short normal resistivity values in the range of 380 ohm meter to 400 ohm meter, and this same layer is having the long normal resistivity data from 780 to 800 ohm meter. So this is the first layer, and it is a weathered zone layer. From the well inventory data which is observed in about 80 wells in the Kurichikulam village, we can infer that the entire village is underlain by the charnakite rocks. So we can infer that this first layer is weathered charnakite, and so by following this same method, I have demarcated various layers for the entire depth of the borewell, and also by using the inferred lithology from the well inventory data from about 80 wells in this Kurichikulam village, I have interpreted the depthwise lithology for the entire depth of the borewell, and I am showing this in this video. This is my interpretation. From the resistivity readings, we can demarcate the total depth of the formations into various layers, but based on the inferred lithology from the well inventory data from the dug wells and as well as the geophysical data, we can infer that there are 4 types of layers. One is the weathered charnakite, the second one is the jointed charnakite, and massive charnakite and fractured charnakite. So these are the 4 types of layers which occurs in this borewell. Next we can do the interpretation for SP data, for which we need to draw a baseline. In SP graphs, the baseline is drawn through the impermeable layers, where the ion movement doesn't take place, which means this line is drawn in the graph where there is no undulation and where the graph is in a straight line. But if we see our SP graph, we have 2 to 3 possibilities to draw a straight line. So in order to find out the exact baseline, we are referring to the resistivity graph. So in the resistivity graph, we should find out the massive charnakite formations or any massive formations with higher resistivity values, and we can consider this as impermeable layers. And if we see the SP graph at the same depth where we find massive formations in the resistivity graph, it will be in a straight line, and we can draw the baseline through this part of the SP graph. So after drawing this baseline, we can see that there are only 2 impermeable layers and all the other layers are permeable layers in this borewell, and this is shown in this figure. From 40 to 50 meters we have an impermeable layer, and then from 83 to 88 meter depth we have a small impermeable layer. This is because only in this depth range we are finding the SP graph as a smooth straight line. In all the other depth ranges we can see undulations, which means those layers are permeable. In this borewell, there are many fractures and joints throughout the entire depth of the Charnakite formation, which is the reason for permeability. And then regarding the water quality, from the ground surface up to 38 meters, the borewell water has less TDS compared to the water inside the rock formations, surrounding rock formations. This is because the undulations are seen to the left side of the baseline. And then from 38 meters up to 90 meters, we have the higher TDS in borewell water compared to the water present in the surrounding formations. This is because in this depth range, the undulations are seen on the right side of the baseline. And again from 90 to 100 meters depth range, we have the borewell water with lesser TDS compared to the water in the surrounding formations. As in this depth range, we can see the undulations are on the left side of the baseline. And finally, we are going to see about the lateral resistivity graph, which is in blue color. Here we can observe that the lateral resistivity values are greater than the long normal resistivity values at the massive Charnakite zones, and this ensures that these massive Charnakite zones are highly impermeable. As we know that the lateral resistivity values are the values of the surrounding formations within the radius of 48 inches and as well as within the thickness of 48 inches at a particular depth of the borewell. And if this lateral values are greater than the long normal, which means that those massive rock formations are highly impermeable and showing high resistivity, which also means that there is no water in these massive formations. So from the interpretation of the resistivity logging data, we have reported the depth-wise lithology of the entire borewell, and also we have demarcated the various permeable and impermeable layers from the SP graphs, and also we have demarcated the freshwater zones and that is the zones with less TDS in the borewell as well as the formation water with the help of the SP graphs. And that's all. Thanks for watching.